In this, we're starting to apply what we've learned about IMFs to situations that help us to explain states and changes of states. With the halogens, fluorine and chlorine near the top tend to be gases at standard temperature and pressure. Bromine is a liquid, iodine is a solid, and astatine and others would also be solids. All of these molecules are perfectly nonpolar, sharing electrons exactly equally. Therefore, they're held together only by dispersion forces, and dispersion forces increase in strength with an increase in polarizability, which is based upon the total number of electrons. So here we'd be going from 9 to 34 to 70 to 106 electrons. Down that column, more electrons, more polarizable, stronger dispersion forces, and therefore more condensed state or molecules sticking together better. The diagram to the right is a phase diagram. We won't ask a lot of questions or have to describe these, but it is a good chance to connect to IMFs. Over here on the left, we are at the lowest temperature, and regardless of pressure, the lowest temperature corresponds to the solid state. The particles are moving most slowly, so whatever the IMFs between them, whether it be dispersion all the way up to hydrogen bonds, or a similar diagram would be true for ionic or any state or any type of particle, the lowest temperatures would correspond to the solid state, molecules sticking together and staying together. As we go to higher temperatures, the molecules move more freely. In a high pressure situation, we are still forcing a lot of them into a low area or a lot of particles with a lot of collisions. They're still likely close enough together that they would stay as a liquid. That's what we would see right here in the high pressure area above, for this instance, 1 atmosphere. If we are in a low pressure scenario, we would see fewer particles close to one another, we would see more spread out, and we would see less attraction between particles, which corresponds to a gas. So here, an important thing is the speed of the particles and the pressure as it corresponds to how close or far apart those molecules are. But it is important, no matter what state we're in, we do have the same type of IMFs. It's just the strength is determined by the proximity of those molecules. And as temperature changes, the ability of the molecule to overcome that attraction through its own kinetic energy. When we compare boiling and evaporating, both are a change from liquid to gas. Both require overcoming intermolecular forces. Both are endothermic, taking energy in. The biggest difference between these isn't whether we're heating it up or whether it's happening fast or slow, it's how much vapor we are producing. If we are producing vapor at a relatively low amount compared to the amount in the air, that would be evaporating. When water evaporates either from the sun or just off of a table or a spill off of the floor, it's evaporating because we have far more pressure from the air than we do from the water vapor that has evaporated. When we take a pot and we boil it, or a beaker on the hot plate, the area above that has as much vapor pressure as the atmospheric pressure of the air. If we had a closed container, we could see and or prove this as the pressure would go up a lot. But when it's an open container, we would be looking at, or maybe even seeing, that steam up there. But that vapor pressure is the difference. But what's important in both cases is input of energy, increasing distance between particles, and therefore creating a vapor. Kind of connecting to the previous two, when ice melts and water boils, we still have the same IMFs, whether water is ice, liquid water, or steam. It's just a matter of how strongly are they able to keep the things in place. As a solid, the molecules are close together. The force of attraction is enough that the particles don't move around, but only vibrate. When they melt, we have to give it more energy to get the particles moving more freely. But from a solid to a liquid state, there isn't a big increase in distance. And it even varies from one substance to another, how much that changes. Some things, the density of liquid and solid are almost identical. But what happens there is the molecules are definitely moving fast enough that they're overcoming that attraction and they're staying in motion, We could think of this in terms of friction, inertia, momentum, lots of different descriptors there. But the idea is that they're moving while still close together. We may have a similar strength of IMF, although probably not exactly the same. Our Q1 and Q2, the amount of polarity hasn't changed. Maybe the distance between them has slightly. But when we boil, and this is true for water and everything else, we are moving our particles very far apart. There's a big difference in the distance, as we would see it in the Coulomb's law equation. The Q's are the same, but they're so far apart that that force of attraction is almost zero. So we need to add enough energy to overcome that attraction to increase the distance that much. Our next example might require a little bit more information when you first look at these molecules. You likely would be given this information, maybe the states, maybe the names, maybe something more familiar. But we would recognize that CH4, because it's nonpolar, only has dispersion forces. Therefore, it's got the lowest IMFs and the lowest boiling point. The CH3OH, that would be methanol. That's normally a liquid at room temperature, so it's a higher boiling point because it hasn't boiled yet. It has dispersion, but it's also polar with hydrogen bonding, so it's higher. The next one, and these two might be tricky, but C25H52 is a general formula that we might give to wax. In that one, we would know that it is a solid. Even though it only has dispersion forces, it has to have strong enough dispersion forces that it stays as a solid. It doesn't take much energy to melt a candle, but more than my methanol because it is a solid at room temperature as opposed to my liquid at room temperature. So a little bit more information would likely be helpful there if we weren't familiar with those formulas. Here, CaO, we should recognize that this is different. I try to use similar elements and symbols in this, but hopefully we recognize that we have a metal with a non-metal. It is ionic. It is held together by ionic bonds, and we're going to be talking about hundreds or thousands of degrees to melt and way beyond that before it boils. So much, much higher in terms of boiling point. And lastly, the vapor pressure is a very useful measure of IMF strength as well. A high vapor pressure means a large amount of my solid or liquid has been able to vaporize and is colliding enough to significantly cause pressure in the air. Diethyl ether has a vapor pressure of 520. Water has a vapor pressure that is a fraction of that, only 24. That means far fewer particles colliding much less than our diethyl ether. And we'll talk about pressure and vapor pressure in the next several videos, but it's just how much vapor is there? A little, a lot. Even without knowing the chemical formulas, even without knowing the structure, even without knowing the polarity of these, we can still conclude about the IMFs. Much stronger when we are more condensed. So we're not always asked to list the IMFs. Sometimes it's just from data that we're able to explain, predict, and compare things.